Okay, so do you have any questions? Now let's first discuss one more thing that we had kind of missed. How do we define the temperature? We had seen in the zeroth law that, it basically allows us to define a temperature. It says that there is a temperature, but how do we actually define them? We had also seen, for example, we had already used temperature, PV is equal to NKT. What is this T over here? Well, in fact, in a sense, this is how we define the temperature. This is the definition, basically. So we make a thermometer made up of ideal gas. Well, we have this ideal gas over here. Let me just take of course, if the volume is constant, N is constant, K is constant, so this is just a constant. So if we somehow measure the pressure of the ideal gas for constant volume, then we measure the temperature. So we take some reservoir of ideal gas. This is a thin tube. So we fill it with some kind of a fluid. So basically this height, well, actual height times rho is nothing but the pressure of the fluid, pressure of the ideal gas. So what we do is we have this bulb. We bring it in contact with what we want to measure, with the system whose temperature we are trying to determine, and then measure this height, which is actually the pressure, up to a constant. This is nothing but our temperature. Now, of course, there is one trick that we need to do. You see, if we heat it, its pressure increases. If its pressure increases, it will push this liquid, and then the volume will not be constant. So we still need to keep the volume also constant. And to resolve that problem, you have another reservoir. Oops. You basically attach to this one a liquid reservoir. This is all filled with liquid, the same liquid. So you raise or lower this reservoir such that this point is fixed. So for example, if you increase the temperature of the heat reservoir, of the ideal gas, then its pressure will increase. It will try to push that level down, but then you increase the height of your liquid reservoir such that more fluid flows into the tube, so that that level is restored, so that the volume of the ideal gas is fixed, and the number of the ideal gas is fixed anyway, and then you have, by measuring that height directly, you measure the temperature. Now, of course, you have to do some scales, so you have to define some numbers to determine that overall coefficient. Well, let's take there are a couple of scales that we actually use. Let's say the water freezes at this level, and it boils at this level. So if you are Celsius, for example, you will call this level the 0 degrees Celsius, and you will just call this level the 100 degrees Celsius. So it's just putting on some numbers, so that we will have some scale on this column, and from which we can directly read the temperature, rather than doing all this, measuring the distance and doing conversions. Now, of course, you can also measure the temperature in terms of length. It's just the definition of your units. What should be the unit of temperature? And if you look at this thermometer, you can just use the unit of, let's say, millimeters to measure the pressure. That is used, for example, still commonly used when you are measuring the blood pressure. So when you say that your blood pressure is 12 to 8, what you are actually saying is 12 millimeter mercury and 8 millimeter mercury. Your blood pressure just ranges between those values above the atmospheric pressure. So it's basically you are measuring pressure as a length. Here you can measure the temperature as a length. And if you are Fahrenheit, for example, you will say, okay, the water freezes at 32 degrees Fahrenheit and it boils at 212 degrees Fahrenheit. You basically, Celsius divides this range into 100 segments. Fahrenheit divides this difference into 180. Well, why 100? Well, 100 is nice because we are used to the decimal system. But 180 is also nice because it's divisible by many numbers, many prime numbers. So in that sense, it's a nice number. If you like, you can just say, okay, the altos are majority over here. What is one of your favorite number? 3. Okay, so alto decides that he will call this as 3 degrees alto. What's your favorite number?
Let's say 70.
70? Yeah. Okay, and then Ertan and alto and Ertan decide to call this scale as 70 degrees alto. So you want to divide this range into 67 segments. Well, 67 is not a nice number, so I'm afraid nobody will pick up with your scale. Too bad. And then, the conversion is kind of trivial if you think in terms of the lengths. So let's say you have some temperature. So basically it tells you that this is the height of your column is this one. Well, the height of that column to the total height should be the same, whatever units you use. That fraction, that dimensionless fraction should be the same. So let's say this is, let me call this total height h0. This height is h. So h over h0 will be your temperature in Celsius units minus 0 degrees Celsius divided by 100 degrees Celsius. So this is just that ratio. But that ratio is also the same thing as the temperature in Fahrenheit units minus 32 degrees Fahrenheit divided by 180 degrees Fahrenheit. 180 is the total length of the column. Or you can also say that this is equal to your temperature in units of degrees alto minus 3 degrees alto divided by 180 degrees, no, not 180, 67 degrees alto. So this will just allow you to change from one unit system to the other unit system. Now, of course, there's some conspiracy theories, many stories about why Fahrenheit chose 32 degrees Fahrenheit and 212 degrees Fahrenheit. Well, the choices he actually made was 0 degrees Fahrenheit is the temperature of equal amounts of water, ice, and some salt. That was basically the coldest temperature that could be attained at that time. So he just preferred to call that 0. And then he said, okay, so let's have another typical scale you have would be, one thing could be the freezing point of water. And remember, you will be eventually dividing this scale into smaller and smaller parts. So when you have a given length, it's easy to divide that length into 2. And then you can just keep on dividing each one of the parts into 2 equal segments, and then take all those parts into 2 equal segments again. So that becomes, well, favorite number was 2 to the power 5, which is 32. So that's probably why they say that. That's probably why the boiling water of boiling point of water was 32 degrees Fahrenheit. And some other number that is nice as 32, 64. Add 64 to that, you get 96 average body temperature. This is the average body temperature of a human being. That is not sick, of course. So that's probably what they say. That's probably why Fahrenheit chose these scales. And of course, it was kind of, well, that 96 is not exactly more or less, because he also wanted to divide the difference between the freezing point and boiling of water to 180, some round number. So he had to play it a bit, and eventually he ended up with this definition of scales. Now, of course, the temperature appearing over here is none of those. So basically, what the observation was, if you just, well, you kind of have a temperature scale using a measurement of temperature, whichever one you like. Then if you are using Celsius degrees, let's say you already have, you know how to measure the 0 degrees Celsius and 100 degrees Celsius. You can probably divide the range into 2 parts of powers of 2 easily. And then you measure the pressure of an ideal gas thermometer. So what you would get is, okay, at some 100 degrees you have some kind of a pressure. As you lower your pressure, it goes to 0. It changes linearly. That is what the ideal gas law says. This is the other. At 0 degrees, there's still you have some kind of another pressure, and then it's a line. Well, as a physicist, when you see a line, what do?
Then you have a linear theory.
Okay, you have a linear theory, so you extend it to everywhere. And when you extend it, it crosses, well, these are, let's say, actual measurements. You have a linear theory. The pressure depends linearly on the temperature. And then you extend it. And then you see that at some hypothetical temperature, let's say, it crosses the 0. The pressure becomes 0. Well, by definition, pressure cannot be less than 0. So hypothetically, that's at least with this thermometer, that's the lowest temperature you can actually measure, even ideally. So that's what you call the absolute 0. Something like minus 273 degrees Celsius. Well, of course, then you have and you can just try it with different ideal gas thermometers. I mean, you see that slope of that curve depends on the volume of your gas, the number of particles in your gas. So you just pick up a different volume, different number of particles, such that that ratio is not the same. In that case, the slope will be different, but what you observe is still, you get a line, if you extend it, it crosses exactly the same point. So you say that, oh, okay, so that 0 was kind of arbitrary for me. We just picked up water, the freezing point of water, but somehow that minus 273 seems to be more universal. So then you have the absolute temperature scale. So basically, if you would show it over here, you say this is 273 Kelvin, and this is 373 Kelvin. And so you can also just convert it you can just convert the Celsius to 273. You still divide the temperature difference between the freezing point of water and the boiling point of water to 100 segments, but you don't call it the freezing point to 0 degrees Celsius, but you just call it 273 Kelvin. So that is what we use, the absolute temperature scale. That is the T appearing in the ideal gas law. Now, of course, to make our life easier, quite often we will actually measure temperature in not in Kelvin. You can also measure it in terms of joules. You see, we had already seen that the energy of an ideal gas was 3/2 nKT. So this KT has units of energy. So I can choose to measure the temperature in terms of some unit of energy, let's say joule. So I will specify joule as my unit of energy. Then K just becomes 1. K is essentially just a conversion factor. For example, from kilograms to grams, you have this conversion factor 1000. Here this K has that weird number because we prefer to choose to measure the temperature in terms of, let's say, absolute temperature, Kelvin. But what is Kelvin? More fundamental will be some unit of energy. And so we can just use the temperature in terms of joules or maybe better electron volts. Because typically room temperature which is taken to be 300 Kelvin corresponds to 1/40 electron volts. Well, remembering this would allow you to just make some order of magnitude estimates about certain quantities. For example, we will see that at 300 Kelvin, you cannot really ionize gases. You cannot create a plasma. But if you want to create a plasma, typically you need to, the energies that you need to provide to the atoms should be of the order of electron volts. If you consider the hydrogen gas, I mean, the ionization energy of the hydrogen gas is 13 electron volts. So you have to provide 13 electron volts. So if you want to create a hydrogen plasma, well, 13 electron volts would basically correspond to 300,000 or 1 million Kelvin. So when you say that, okay, in the sun is basically a hydrogen plasma, we know that its temperature is at least 1 million Kelvin. Okay, any questions on how we define the temperature? Okay, now, then finally let's start some statistics. Let's start with a very, very simple system. Let's assume we have some container filled with some gas. We just put some gas inside. Let's say that we adjust it such that initially we have a compartment here and we put all the gas molecules in this compartment. And then we just remove the compartment so that the gas molecules are basically free to move. So if you just wait some more, if you look at the velocities of these molecules, let's say this might be moving in this direction, this might be moving in that direction, this downward, this is upward. Well, they will be moving in all directions. Now when we remove the container, some of them will just start moving around. So this will be its trajectory. This one will more or less move up and down. This one will first hit over here, then here. Now if you just follow a single particle, Its motion, at least let's just treat this problem for the time being just classically. The motion is quite determined. So if we know the initial velocity, initial position, which ideally we can know, we can just follow its trajectory, and we know at a given point where it will be. So it's there's no statistics here, it's just a deterministic process. But you see, if you wait long enough, for example, this particle, if you wait long enough such that this particle already makes hundreds of rounds going here and there, this other particle, which is moving up and down, will just go up to the left and to the right just a couple of times. If you kind of pick a random moment, then whichever particle you in fact consider, at that random moment, the probability that a given particle will be on the left, well, let us divide it into two parts. The probability that a given particle will be on the left is 1/2. The probability that it will be on the right will also be 1/2. That's because we are just picking up a random time, and we know that all the particles spend half of their time on the left and half of their time on the right. So we know that at this time, for a given particle, the probability that it will be on the left will be 1/2, the probability that it will be on the right will be 1/2. Now let's ask this question: what is the probability that n of these particles are on the left? What is its probability?
2 to the n minus n.
Well, 2 to the n minus n. This one.
2 to the n over 2 to the n. 2 to the n over 2 to the larger n, I guess.
Well, let's look at certain cases. If this is correct, then the probability that all of them will be on the left, that small n is equal to large n, is 1. So, at least just looking at certain limits, it cannot be this one. Well, we also know certain constraints on these probabilities. So, for example, the probability that n of them are on the left, the probability that none of them is on the left, plus the probability that one of them is on the left, plus the probability that two of them are on the left, etc. If you just sum all the probabilities up to capital N, it should be 1. Well, let me just give you a hint. The probability that one of them is on the left is 1 over 2. The probability that that same particle is on the left is also 1 over 2. Well, in fact, we could have just started with saying the probabilities are P and Q, but the sum of the probability that the particle is either on the left or is not on the left is just 1. You see, the probability that we are looking for is actually this one. You see, first of all, which particles are on the left? We don't know. Well, there are many possibilities. We are just saying that there are small n of them are on the left. So in how many different ways can we choose these n particles that are on the left? It's just that combinatoric factor over there. Let's look at this factor. Given that we know which particles are on the left, n of them are. So for each one, the probability that they are on the left is 1 over 2. So that we know that if small n of them are on the left, the probability that the small n are on the left is just 1 over 2 to the power n. But we are also saying that the remaining particles are not on the left. So we are actually saying that small n of the particles are on the left and the remaining particles are on the right, or not on the left. The probability that each one of the remaining particles is on the right is 1 over 2. So we have capital N minus small n of them. So the probability that all of them will be on the right is just 1 over 2 to the power capital N minus 1 minus small n. So this is the probability that at a given instant, small n of all the particles will be on the left. Now, let's see what this function looks like. For us, it will be important. No, I had already defined it. So this is the gamma function. No, it's too small. Okay, so this is the gamma function. This is basically capital N factorial. This is the small n factorial. This is their difference factorial. And then I have 1 over 2 to the power small n times 1 over 2 to the power capital N minus small n. This is the function I define in Mathematica. Well, the reason why I use the gamma function is just I want to make a smooth plot. So this gamma function is defined for all numbers, except on negative integers. Factorial is defined only for positive integers. Now let's see, I can just plot this function as a function of the small n. The small n can take values from 0 to capital N. Well, I'm scaling my probability so that on the middle is 1, just so that we will be able to see the plot. And I'm also scaling this x-axis so that the x-axis, whatever the total number of particles is, goes from 0 to 1. It's basically the fraction of the particles on the left. So this is for when the total number of particles is 10. You see, the maximum is at 0.5. So half of the particles are on the left and half of the particles are on the right. And then the probability basically drops to 0 as we go to the extremes. All the particles are on the left or none of the particles are on the right. But still, the probability, for example, of, let's say, having 20% of the particles on the left is something like 0.15, 15%. It's not a very small probability, so it's quite possible to observe a given state in which only 20% of the particles are on the left. So if we keep tracking the systems, it will be quite likely that we will observe such a configuration of the particles. Now let me increase the number. Now I have 100 particles. And this is how the probability distribution looks like. Now if we have 100 particles, you see that still the maximum is at 50%. The 50% of the particles is on the left and 50% is on the right. But you see the probability of observing, let's say, 20% of the particles on the left and 80% on the right is practically 0. So if we keep observing our system of 100 particles, if you want to observe just once a configuration in which the left and the 20% is on the left, we have to wait quite a long time because the probability is almost zero. Now, still, there is a significant probability that there will be only 40% of the particles on the left, and 60% will be on the right. Let's say that probability is something like 10-11%. Now let's increase the number. This is 1,000. I have just 1,000 particles. You see, the probability distribution becomes quite peaked. Now, the probability of observing only 40 particles on the left is almost zero. What I will observe is the most probable configuration will be 50% is on the left, 50% is on the right. And the probability of observing even a 5% deviation, let's say 5% deviation is 45 and 55, this range. Probability of observing a deviation larger than 5% is zero. Practically, we will not be able to observe such a configuration. So what we see here is that the probability is maximum when half of them are on the left and half of them are on the right. And the probability of deviation from that maximum probability basically goes to zero as we increase the number of particles. You see here the number of particles is just 1,000. Keep in mind that in statistical physics, in the problems that we will be applying our statistical concepts, the number of particles we have is typically of the order of 10 to the power 23 or even more. So you can see how narrow this probability distribution will be. So although we will be always talking about probabilities, the probabilities we will be talking about will be 1 or 0. So for, let's say, 10 to the power 23 particles, I can definitely say that half of the particles will be on the left, half of them will be on the right. In the sense that the probability of a fluctuation from this value will be almost zero. Now let's try to quantify these values, these observations. So here we have some numerical observations. So the first question I would like to ask is, what is the average number of particles on the left? Well, this will be basically n times PL and capital N, small n from 0 up to large n. This is how we define the probabilities. This will be equal to from n 0 to capital N. Well, let me just put P to the N and Q to the capital N minus N over there. Eventually, I will set P is equal to Q is equal to 1/2 because I'm just assuming that I'm dividing my container into two equal parts. You don't have to assume that you are dividing into two equal parts. You can just say that, okay, I divide it such that on the left there is the 1/3 the volume, on the right there is the remaining volume. Times N. Now I will do a trick here. So this is nothing but from N is equal to 0 to capital N, this combinatoric factor derivative with respect to P of P to the power N, Q to the power N minus N, let me also multiply by P after taking the derivative. Because if I do that, when I take the derivative, it will bring down a factor N, but the power of P will be N minus 1. So that's why I multiply with P. This will be P times the derivative with respect to P from N 0 to capital N, P to the N, Q to the N minus N, or P times derivative with respect to P of p plus q to the power n. Now I can just take the derivative. Average n is p times n times p plus q to the power n minus 1. Now keep in mind that p plus q, no matter how you divide your volume, p plus q is just 1, because p is the probability that your particle is in your volume, and q is the probability that it's not in your volume. So it's either in my volume or not in my volume, so the total probability will be just 1. Now basically this is valid whatever the value of p is, so whatever volume fraction we are studying. So the average value in our case is just n over 2. Well, that we can also see it over here. You see, whatever the total number is, the probability distribution is symmetrical around the middle point. So when you calculate the average number of particles, well, it's still the average, in the middle, 50%. Now, the important thing that we wanted to see over here is how much they deviate from this average value. You see, for small number of particles, the deviation from the middle value can be significant. There's a large probability that we will observe a significant deviation from the average value. Now, when we go to larger numbers, we say that the probability of observing a significant deviation will be very small. So can we also show it in this example? Now, the deviation, well, let me just call this n bar. I will also use this bar to denote the averages. So this is the deviation from the average. Well, if we just take the average of this one, this is the average of n minus the average of the average of n. Average of n minus the average of a constant is just the constant itself, but this is 0. Well, that's kind of expected because that deviation from the average can take both positive or negative values. But we can prevent that. We can make sure that the deviation we are talking about is always positive by looking at its square. So this will be definitely non-zero. And it will give us a value how much the n deviates from the equilibrium. Well, let's just try to analyze it a bit first. This is n squared minus twice n average plus n average squared. The average of n squared minus twice the average of n average plus n average squared. Well, this is equal to n squared average minus twice. Well, this is just constant. I can take it out of the averaging. Plus n squared average. And keep in mind that this is also an average. So this is nothing but the square of the average of the square of the numbers minus the average of the numbers squared. This is what's usually called the standard deviation, the square of the standard deviation. Now let's calculate this n squared. Now what we had, this n squared average, well, I will basically use the same trick. This is from small n to capital N of n squared times p to the n times q to the power capital N minus n. This is equal to 0 to n p to the n q to the n minus n. I will take the derivatives of p such that it will bring this n squared factor. Now let me take the derivative with respect to p once. It will bring a factor n. Now the power of p to p is n minus 1. So if I take its second derivative, it will not bring n minus 1. Well, let me just take the second. It will not bring another factor of n, but it will bring a factor of n minus 1. So let me first multiply by p. so that the power of p is restored to n. Then I take the derivative with respect to p again. So it brings down a factor of another factor of n. And then the power of p is now n minus 1. Let me multiply with p once more. So this is the average of n squared. P times the derivative with respect to p of p times the derivative with respect to p of p plus q to the n. Now let me take those derivatives. This is, well, let me first take this derivative. Keep in mind that that derivative is acting everything on the right. So I take the derivative of this factor p first, so that becomes the second derivative with respect to p of p plus q to the power n. No, sorry. So I took the derivative of this one. So this is what I have. Plus p squared, the second derivative with respect to p of p plus q to the power n. This is equal to, now let's start with this one. This is p times n times p plus q to the power n minus 1 plus p squared. Well, if I take twice the derivative, it is just n minus 1 of p plus q to the power n. N minus 2. So this will be p times n plus p squared n squared minus p squared times n. Which is p minus p squared, or let's p times 1 minus p times n plus p times n squared. So n squared average is n average squared plus p times q times n. Or n squared average minus n average squared is pq times n. This is the deviation from equilibrium. Let's see what percentage does it deviate from the equilibrium value, from the average value. So this is pqn over p squared n squared. So basically the import, this is q, let's say q over p times 1 over n. So this is delta n squared over n average squared. This is proportional to 1 over n, which basically tells me that delta n over n average is proportional to 1 over square root of n. So basically it tells me that this delta n is how much it deviates from the equilibrium, from the average value. And we see that the fractional deviation goes to 0 as the number of particles goes to infinity. So this is basically what we had observed over here. You see, as the number of particles gets larger and larger, there is no significant deviation from the average value, which is the most probable value. So this will be the basic idea of all the statistical mechanics that we will do. So we will be dealing with, well, all the particles that we will be studying, they are following definite laws. So they are not moving randomly. But we will assume that they are moving randomly. And at the end of the day, the laws that we will derive will not be probabilistic, because the probability of observing a deviation will be zero, practically. Because the deviations, the fluctuations will just go to zero as the square root of the number of particles, which will be typically of the order of 10 to the power 23. Well, let me just make one correction to this deviation. It doesn't change my conclusion, but to be more formally correct, let's say, if you don't define P and Q such that their sum is 1, so here when I was taking the derivative with respect to P, I was assuming that P and Q were independent variables. And hence, their sum is not necessarily 1. So I have to divide by the normalization, which I didn't divide over here. I have to divide, to define this average. The average will not be actually this one, but the average will be divided by P plus Q to the power n. Well, this will be important in the derivatives. So you see here, there will be essentially 1 over P plus Q to the n, an overall factor. But, well, they will not change the result significantly. The result will be the same.
By the way, P and Q are dependent, right?
Well, you see, it depends. Here I'm assuming that P and Q, initially I'm assuming that they are independent. At the end of the calculation, I'm just setting them to be their sum to 1. Since I'm assuming they are independent, this probability distribution that I wrote down is not properly normalized. The sum is not 1. So that's why I need to divide those. Well, okay, so probably that's not the correct place to put that factor. This is still correct, but here I need to divide by P plus Q to the power n to properly normalize them.
What I want to say is you have taken partial derivative with respect to P. Just ignoring that they are dependent.
Well, if I divide by that factor, P plus Q to the n, I can assume them to be independent. But you are right. Formally, this derivation is flawed in the sense that, as you said, I'm taking the derivative with respect to P, ignoring the dependence of Q on P. If I want to ignore that dependence, I have to divide by this factor P plus Q to the n. But of course, since it's just out of the summation, and hence it will be out of this derivative. So basically, if I correct this derivation here, I need to divide by P plus Q to the n, here by P plus Q to the n. So here I have to divide by P plus Q to the n. But this result doesn't change because basically P plus Q is 1. Now I can set, after this step, I'm just setting P plus Q is equal to 1. Before they were independent, at this step I am taking them to be dependent. And similarly in the calculation of n squared, again basically the same thing. So I have to divide this thing by P plus Q to the n. These are my probabilities. So the results are basically the same, but formally I have to divide by this factor. to assume that they are independent. So questions? So let's give a 10-minute break and then we will continue.